find the volume of the solid formed by rotating y is equal to lim of x about the x-axis up until x is equal to 3. So our natural log of x graph looks something like that, okay? And it follows this line over here, and it intersects the x-axis at x equal to 1. And we followed it all the way up until x equals to 3. Okay, but now rotating this about the x-axis, we get a shape that looks something like what I've already drawn. Okay, so essentially, this point is closer to us, and this point over there is further away from us. And I hope you can see this in 3D. Okay, so in order to find the volume, we have to integrate from x equals to 1 until x equals to 3. So our volume is going to be equal to the integral from 1 to 3. And now what we're going to do is we're going to take disks, all of these little disks that are contained in here, and each of these little disks will have an area. And those areas, if we sum them up, all of them, the infinite number of them that are contained between x equals to 1 and x equals to 3, if we sum them up through integration, then we'll get the volume of what is formed, of the solid that's formed when we rotate the natural log of x about the x-axis. Okay. So then the question is, what is the radius of each of these circles? Because if we're finding the area of each of them and we're summing them up, we have to know the radius. So the radius is simply going to be the natural log of x. And the reason why is because we're going from x to what x is being transformed to, or the y value of x. So for example, at this point over here, our x may be somewhere closer to 3 than 1. It's an arbitrary point, it doesn't matter. And we plug that point into the natural log of x, and out will come the y value at that point. And the y value at that point is equal to the distance to the x-axis, which gives us the radius of the circle that goes through that point. And if we can find the radius of the circle through that point, we can find the area of the circle. Okay, so carrying on with the integral, we are looking for the integral from 1 to 3 of, now the area of a circle is pi r squared. So we have pi times by the radius, which we said was the natural log of x, and that's squared dx. So now all that's left to do is for us to solve this integral. So what we're going to do is we're going to take our pi as a constant. From 1 to 3, the natural log squared of x dx. Okay, now we're going to solve this using integration by parts. So if we let u equal to the natural log squared of x, and we let dv equal to dx, then the derivative of u in terms of x is going to be 2 natural log of x over x, and integrating this, we'll get v is equal to x. And the reason why this is so is because we use the chain rule first. So the outermost function is the natural log squared. So we decrease the power by 1 and we multiply by the original power. So it's 2 natural log of x. Then we do the derivative of what was inside the square, which was the natural log of x. And the derivative of the natural log of x is 1 over x. So 2 natural log of x over x. Okay, now rewriting this, we get pi into u times by v, so x natural log squared of x, minus the integral of v du. So that's x, 2x times by the natural log of x over x. Then of course those x's will cancel, and we can take this 2 outside. We're left with the natural log of x dx, and this whole thing is being integrated from 1 to 3. Okay, so now we're going to use another integration by parts for the natural log of x. So instead of using v and u now, we can use s. So s is going to be the part that's easier to differentiate, and this time it'll be the natural log of x. So the derivative of s in terms of x is going to be 1 over x dx. And then dr is what we would use initially for dv. We'll use dr in this case, just so that we don't use v twice. And that'll be equal to dx. Okay, so then r must therefore equal to x. Okay, then solving this, we get pi into x natural log squared of x, that remains the same, minus 2 into, okay, now it's s times by r, which is x times by the natural log of x, minus the integral of r ds. So that's x over x dx, which is just 1 dx. And then 1 dx, the integral of 1 dx is simply x. Okay. Now, this was integrated from 1 until 3. All right. Now what we can do is we can simplify this, or expand it, rather. So distributing this pi, we get pi x natural log squared of x minus 2 pi x natural log of x plus 2 pi x. And that's integrated from 1 to 3. All of that. Okay, now substituting in 3, we get 3 pi times by the natural log squared of 3 minus, and now this x times by this 2, and when x is equal to 3 is going to be negative 6 pi times by the natural log of 3, and then that's plus 6 pi, because we substituted in 3 there for the x. And then we're going to subtract when we substitute in 1 now. Okay, so substituting in 1, we get pi times by the natural log squared of 1, and then that's minus 2 pi times by the natural log of 1, and that's plus 2 pi. So that was all when x is equal to 1. Okay, so in here, we notice that the natural log of 1 is 0. So both of these terms here are going to be equal to 0. So I can just erase them. Okay, so now we have minus 2 pi, but here we have plus 6 pi. So we can simply write plus 4 pi. And then this is going to be units cubed because it's volume. So that is the solution to the initial integral and the solution to the volume contained in this solid, where natural log of x was rotated about the x-axis up until x is equal to 3. Thank you for watching.